So we would solve the problem which I have introduced towards the end of the last class, which is you have some sort of a microprocessor which is built on a rectangular die whose sides are 2 centimeter and 1 centimeter, which has to be kept at 105 degrees centigrade, and you are going to have airflow either on this along this length L or along the width W. So you need to calculate what is the velocity of air, in order to maintain the temperature at 105, in which way we should orient the chip. If the flow is, let's say this is my L and this is my W, so if we have the velocity in this direction, this is L, this is W. If the velocity is in this direction, should I keep it like this or should I keep it like this in order to have the maximum transfer of heat? So this decision is what we need to make. So the first thing we have to understand is, when we have, let's say this is a flat surface and I have flow of air over it. Initially the thickness of the boundary layer is going to be very thin, and then at certain point it reaches turbulence and then it starts to increase in this fashion. Now if you draw the value of heat transfer coefficient, and this is x, along x over the initial part of the flow, the thickness of the boundary layer is going to be very thin. So if the thickness of the boundary layer is going to be very thin, then the resistance to heat transfer from the solid to the air, if we assume the solid to be at a higher temperature, the resistance is going to be low. So you can start with a high value of H at the beginning. As we move along, the thickness of the boundary layer will keep on growing, and therefore the resistance to heat transfer would increase, and the heat transfer coefficient is nothing but the inverse of the resistance to heat transfer. So resistance is going to be minimum at this point, and it's going to progressively increase as the thickness of this is increased up to the point when it is the laminar turbulent. This is the junction between the laminar and the turbulent. So this is how it would look like. So your value of H would start at a high value, and then it would probably keep on decreasing, and after we reach this point, so this is, I call this as X transition. At this point you are going to have turbulent flow, and the way we define it, as if up to this point I have perfectly ordered laminar flow, and beyond this point it's going to be random mixing which are taking place inside the boundary layer. As I told you before, in reality it doesn't happen like that. You do not have a clear-cut demarcation between laminar flow and turbulent flow. So you start as laminar, but as you move as your X increases, the disturbances present in the system will also increase, and the transition from laminar to turbulent is not going to be sharp. Actually it's not going to be at a specific X, rather over a certain delta X it will slowly go from mixed, well mixed, very well mixed, and then it will become turbulent. But for our convenience, what we do is we put a value of Reynolds number to be equal to 5 into 10 to the power 5, and we say everything before that is laminar and everything beyond that is turbulent. So up to this point the flow is ordered, and from this point onwards there is going to be a lot of intermixing. The ADs are going to take the momentum, energy and species. So there is going to be not only heat transfer by conduction, it is going to be vigorous heat transfer by convection as well, and the boundary layer will grow accordingly. Same with hydrodynamic boundary layer or species boundary layer. So in this figure, then whenever I heat transition, the value of the heat transfer coefficient will increase again. So up to this point, what you have is laminar flow. Beyond this point is turbulent flow. In the laminar flow, the value of H decreases as the thickness increases, but at this point, since you are going to have lot of intermixing, so heat transfer is going to be enhanced and you are going to have turbulent flow, and the heat transfer coefficient starts to increase and it will reach some sort of a plateau after that. Okay. But initially you will have the maximum amount of heat transfer. So this has to be kept in mind while solving problems and while thinking about how to orient my surface in order to get the maximum heat transfer. Now if you think of the surface over which this is the chip, so I can either do it in this form or I can keep it like this. The flow is over here or the flow is over here. Now I think you would be able to answer which orientation is going to give rise to higher value of heat transfer coefficient. What we have seen from H versus X curve is that you would like the boundary layer to be thinnest on the region over which the flow takes place. So if you take the case 1 over here and case 2 over here, obviously case 2 is going to have the thinnest boundary layer as compared to case 1. So the case 1 will have a higher average thickness of the boundary layer as compared to case 2. So you would always like to orient your surface in this way such that the smaller length is exposed to flow. The situation would be different if you have transition. That means after passing through some distance it becomes turbulent. Then a clear cut solution of whether to have it in this way or in this way cannot be made. But if it stays laminar, if you are working in this zone, then it's always better to have the smaller side exposed to flow. So we start with first, this is a very, once you understand this, there's nothing in this problem. So at steady state, what you are going to have is heat generation must be equal to heat out, and heat generation is the Q dot, the amount of heat generation per unit volume times V would be equals H bar times AS Ts minus T. So here AS is independent of orientation. Here this is length, this is width, this is length, this is width. So your AS would always be equal to L times W, but the value of H bar would be different based on how you have placed it over there. So the heat transfer coefficient would be equals Q dot V by AS Ts minus T infinity, and you know the value of Q dot is provided. So the value of Q dot is provided here. So this is your Q dot to be 5 into 10 to the power 5 watt per meter cube. The value of T surface must be equal to 105 degree. The chip is cooled and the T infinity is going to be equal to 20 degree centigrade. So the air is 20 degree and it cannot exceed 105. So your Ts maximum value would be 105 and T infinity is always at 20. So and AS is simply L times W. So you should be able to calculate what is the value of the average heat transfer coefficient, which would be 20.6 watt per meter per Kelvin. So the value of H is known to you. What you need to do is what is going to be the velocity of air which is going to flow over it. So your Nusselt number relation is simply H bar L by K, which if we assume it to be laminar flow, we do not know whether it's laminar flow, we will check later on, but the laminar flow, the relation is REL to the power half times Prandtl number to the power 1 by 3. So your V infinity, since this Nusselt number average value based on the length is 0.664 REL to the power half times Prandtl to the power 1/3. This contains the velocity. So, the velocity width of air flowing over the surface would be nu by L times HL H bar L by 0.664 K times Prandtl to the power 1/3 to the power 2, where this would turn out to be 0.55 meter per second. Okay. So, the important thing over here is what is going to be the length scale, what is going to be the length scale that we have here, and this and this one. Okay. As I mentioned, you would like the flow to be in this direction over the shorter side, over the shorter side. So, if you want it to be the shorter side, in order to obtain the flow rate over here, the value of L would simply be equal to 1 centimeter. So, as you have seen in this case, this is 2 centimeter and this is 1 centimeter. So, you want to have the flow in this direction. So, the corresponding length scale would be equal to 1 centimeter, and when you do that, you are going to find out the value of the air velocity required for this case is 0.55 meter per second. One more point that and then we would stop any further discussion on this, is we are calculating the value of H bar. Now, this value of H bar simply tells you that it is a length average H, since H bar is simply equals 1 by L 0 to L H, which is a function of x times dx. So, on this material, your value of H is going to Hx is going to be different at different points. Okay. And what we are using in these correlations is the average value of H. So, unless this material has a high thermal conductivity, there would be local variations of temperature on the chip. So, since I am basing all my calculations on the average value of the heat transfer coefficient, so I understand that the value of local heat transfer coefficients can be different at different points. Since the temperature difference is known, so your value of temperature difference is since Hx is varying, so T on the surface will also vary. So, if the material of this semiconductor or material of this rectangular die, if it does not have a high thermal conductivity, then you are going to have different temperatures at different points. So, if there are different temperatures at different points, then there is going to be thermal stresses which are going to generate on this die, which is going to be detrimental to the overall structural integrity of the chip, which is mounted on this rectangular die. So, one has to keep that in mind while designing a heat sink composed of an extended surface in the form of a rectangular die, in the form of a die on which the microprocessor is going to be placed. So, the purpose of this problem is to give you an idea of how does H vary with length based on whether you are in the laminar zone or you are in the turbulent zone. So, that more or less completes my tutorials on analogy. Then, as I told you before, I am going to discuss something on the momentum integral equation. The momentum integral equation, its use in order to obtain what would be the pressure drop, what would be the velocity, what is going to be the concept of displacement thickness, and several other associated issues. So, I have decided to solve a few problems on momentum integral equation. If you recall, the reason we have introduced momentum integral equation is that an analytic solution to most of the boundary layer flow problems was very difficult to obtain. it was possible only for the flow over a flat plate, which is a zero pressure gradient situation, and even in that case an analytic solution was not possible. We had to resort to a numerical solution. So, considering that, and with the application, when we consider the application, we do not need the velocity at every point. We are happy if we can find out somehow what is going to be the shear stress of the flowing fluid on the surrounding solid surface, and what is the boundary layer thickness at any given axial location. So, we were looking for solutions which would give us a quick method to obtain these two parameters, the thickness of the boundary layer and the shear stress exerted by the flowing fluid on the solid substrate. So, then we have introduced the concept of the momentum integral equation. So, we started with the very basics, on which the forces on the control volume can be expressed in terms of the momentum, the momentum which comes in to the control volume, and the expression for the momentum integral equation which you have obtained, it contained a term which would give you the transport of momentum due to actual flow, and from that point onwards we also introduced the concept of what is the displacement thickness, because the boundary layer thickness is difficult to estimate experimentally, since the velocity profile asymptotically approaches the free stream velocity. It's difficult to demarcate the point at which the velocity becomes equal to the free stream velocity, or 99% of the free stream velocity. So, again here we also used the concept of integral thicknesses. The integral thicknesses are nothing but thicknesses defined in such a way that any integration is just summation when summation over a large number of intervals. So, if by any means I can define my thickness in such a way that towards the end, where the flow approaches the free stream, the terms that are there in that extended summation, the influence of those terms is negligible on the overall thickness. So, integrand vanishes automatically near or at the free stream. So, if we can define a thickness in that way, then that thickness will have marginal experimental error embedded into it, unlike the case of the boundary layer thickness, which has a large error. So, two thicknesses were introduced, one is displacement thickness and the other is momentum thickness. So, the displacement thickness was delta star by delta was 0 to 1 minus small u by capital U times d eta, where eta is the distance from the solid wall, okay, and u is the local velocity and capital U is capital U is the free stream velocity. So, the displacement thickness is simply given as delta star is, if I make it from 0 to delta, it would be easier to understand. Delta star is going to be 0 to delta 1 minus small u by capital U d eta. So, if you express it in as a summation term, you can see that u tends to u as eta tends to 1, that means y tends to delta, eta is nothing but y by delta. So, as y tends to delta, u tends to capital U, and this entire term becomes very small. So, the definition of delta star is such that you do not have any effect of the errors associated with u when you approach the free stream. So this has given us the definition of delta star, the the displacement thickness, and also theta, which is momentum thickness. And physically, delta star can be thought of like when you have a flow over a surface, there is going to be a formation of a boundary layer. Since viscosity is important inside the boundary layer, the flow inside the boundary layer is going to be slower as compared to the flow outside, which does not have any effect of viscosity. So inside it is viscous flow, outside of which it is inviscid flow. Inside the boundary layer, the fluid travels slower. Outside of the boundary layer, the fluid travels faster. So if that's the case, then the presence of the boundary layer reduces the mass flow rate near the solid surface. And how do I take that into account? If I want to convert this condition where I have a boundary layer and a free stream. So from here to here I have viscous flow, from here to here I have inviscid flow. I would like to change that to this case where everywhere it's inviscid flow. So for the situation where viscous flow, inviscid flow is to be replaced by inviscid flow everywhere, then the way I can do it is in the real flow I am going to if I raise the platform, if I raise the solid plate by a distance equal to delta star such that it's going to be exactly equal to the reduction in mass flow rate due to the presence of viscosity. So this is my situation where I have viscous layer, inviscid flow, and this is inviscid flow. I am going to raise this by some distance which is going to be equal to the reduction in mass flow rate that is taking place inside the boundary layer as a result of the presence of viscosity. So displacement thickness is the distance by which the flow area has to be restricted in an inviscid flow to obtain the same reduction in mass flow rate as you would have obtained in viscous flow inside the boundary layer. So that is the concept. Based on this concept, we are going to solve the next problem. So here I have a square duct and the size of the duct is 0.3 meter and this is also 0.3 meter. Air is flowing through it. So air flows through this duct which has a density equal to 1.23 kg per meter cube. The velocity is going to be equal to V1 is going to be equal to 24.4 meter per second at the beginning of this section. Okay, so this is 1, this is 2, this is 24.4 meter per second, and it is turbulent boundary layer everywhere. So we have turbulent boundary layer at 1 as well as at 2, and the turbulent boundary layer they are going to form on all sides. So they are going to form on all four sides which are forming this duct. At the beginning at 1, the thickness is equal to 20.3 millimeter entry, and at exit this thickness is equal to 30.5 millimeter. Okay. The boundary layer profiles follow 1/7 power law. Okay, so if this is 1/7 power law, you have to find V2, which is essentially free stream velocity at 2, and the delta P static pressure, change in static pressure between 1 and 2. So, this is what you have to find out. First of all, if since 1/7 power law profile whenever I am trying to find out delta P, I am essentially going to use Bernoulli's equation. Whenever I use Bernoulli's equation, I understand that Bernoulli equation is valid for inviscid flow. So, this is a case where you have viscous flow because you have some boundary layers which are forming on all four sides. So, somehow this situation is to be converted to an inviscid flow, and if it is inviscid flow, only then I can use Bernoulli's equation. So, to convert a flow situation which has a finite boundary layer thickness and then a free stream beyond that, in order to change that to inviscid, I have to use the concept of displacement thickness. Because if I can introduce the concept of displacement thickness, then essentially the flow becomes inviscid everywhere. So, that is the beauty of using an integral approach, a different the approach where delta star, the displacement thickness, is used, because if I reduce my flow area by delta star from all four sides, then whatever velocity, whatever flow I have in that, it can be treated as inviscid, because the effect of reduction in mass flow rate because of the formation of boundary layer has already been taken into account in the value of delta star. So, therefore, the available flow area can be reduced by delta star from all sides. So, if this was L initially, the new area that is going to be equal to L minus 2 delta, since it is forming from both sides on this side, and L minus 2 delta from the top because of formation of boundary layer at the top and the bottom. So, my new flow area right now will become not L square, but L minus 2 delta whole square. So, that is the beauty of the concept of displacement thickness, is that you convert a viscous flow situation into an inviscid flow situation through the incorporation of the displacement thickness. So, first thing one needs to do is, what is the expression of displacement thickness, what is the value of displacement thickness if 1/7 power law is valid. So, that is what I am going to do in here. So, 1/7 power law profile would simply give you delta star is 0 to delta, by definition u by u times dy. So, if I take delta outside, so it becomes 0 to 1 minus eta to the power 1/7, because u by u is eta to the power 1/7, since it is 1/7 power law, as I have mentioned before. So, this becomes equal to, if you perform this integration, you would see that delta star is going to be equal to delta by 8. Okay. You know the values of delta at these 2 points. So, you know what the values of delta star at this point. So, A effective, as I explained, is simply going to be whatever be the height, whatever be the length, whatever be the size of this duct minus 2 delta star whole square. So, if you use equation of continuity, A1 V1 is equal to A2 V2, what you are going to get, the velocity, the first thing that you have to find out is what is the velocity, find what is V2. V2 would simply be equals V1 times A effective by A2 effective. So, this would be V1 times H minus 2 delta 1 star by H minus 2 delta 2 star whole square, which would be equal to 24.4, and the value of H, I will simply write the value of H is equal to 0.3, and delta 1 star would be equal to 20.3 divided by 8, and delta 2 star from here and here would be equal to 30.5 divided by 8, all in millimeters. So you put the value of delta 2, delta 1 in here, and what you would say is V2 is equal to 24.83 meter per second. You should put the numbers in check, and therefore you start with a value of 24.4, and at location 2 you are going to get V2 equals 24.83. Okay. Since you have the formation of the boundary layer, it keeps on growing, so your value of delta 2 will also be more. If value of delta 2 is more, you have less area available for flow, and if you have less area available for flow, then from equation of continuity your flow velocity has to increase, since V into A is a constant. So you get the value of velocity in here. The pressure drop P2 minus P1 is simply going to be equal to half rho V1 square minus half rho V2 square. So this is Bernoulli equation, and I can use Bernoulli's equation since my flow is now inviscid. It no longer a viscous flow. So Bernoulli's equation in this form is applicable. So P2 minus P1 would simply be equals half rho V1 square 1 minus V2 by V1 whole square. So that's there. So again P2 minus P1 would be half rho V1 square 1 minus A1 by A2 whole square. This is from equation of continuity. So this can be written as half rho V1 square 1 minus, my area is going to be H1 H minus 2 delta 1 star. The A2 would be equal to H minus 2 delta 2 star, and this whole thing would be equal to the power 4. Okay. So that is going to be this, and when you put the value for rho V1 delta 1 delta 2 and H, you would see that P2 minus P1 would turn out to be minus 12.95 Newton per meter square. So obviously for flow to take place from 1 to 2, the pressure at 2 must be lower than at 1, and therefore P2 is lower than P1, and it is the difference in pressure is equal to 12.95 Newton per meter square. So once again what I have done is I have used Bernoulli's equation between 1 and 2. I can use Bernoulli's equation as long as I use the concept of displacement thickness, and since in displacement thickness the whole flow situation would turn out to be converted to an inviscid flow. So it's by taking V1 constant, V1 outside, it's V2 by V1, and V2 by V1 by equation of continuity is A1 by A2, since A1 V1 is equal to A2 V2, and A1 is H minus 2 delta 1 whole square, A2 is H minus 2 delta 2 whole square. So A1 minus A2 square is simply going to be to the power 4, and in this case you know all the terms rho V1 H delta 1 delta 2, and therefore you should be able to calculate what is the pressure drop between 1 and 2. So we see here that how the concept of displacement thickness allows us to calculate what is the pressure drop between 2 points. The reason I am using the concept of displacement thickness is to convert a viscous flow into an inviscid flow. The moment I convert a viscous flow to an inviscid flow, I can use a simple equation like Bernoulli's equation to find what is the pressure drop. So if we can, mostly for the case of flow over a flat plate, using the initial concepts of momentum integral equation, the concept of displacement thickness, convert into an inviscid flow and use Bernoulli's equation to calculate the numbers. But so this is an example of the use of the concept of displacement thickness. What we would do in the next class is a problem based on the displacement thickness concept, but additionally there we have to use the momentum integral equation as well in order to obtain other relevant parameters. For example, the shear stress exerted by the duct, as in this case, on the fluid which is flowing. So, this problem is about the use of displacement thickness. The next problem is going to be about the use of displacement thickness and momentum integral thickness, which we will take up in the next class.